Tonight, we're going to explore the story of a man who saw the structure of reality more clearly than almost anyone who had ever lived, and was laughed out of the room for it. A man who submitted his doctoral thesis to the greatest physics department in the world, watched the most powerful physicist of his generation dismiss it as meaningless, and then quietly walked away from physics forever. He never received recognition in his lifetime in the way the theory deserved. He never saw anyone take his ideas seriously with the weight it warranted. He died at 51 in his home office, having spent his working life not advancing the theory he had discovered, but calculating nuclear war scenarios for the Pentagon. He asked for his ashes to be thrown in the trash. His daughter honored the wish. And then the rest of physics caught up. Today, the many worlds interpretation of quantum mechanics, the theory Hugh Everett III proposed in his 1957 Princeton PhD thesis, is considered by a significant and growing number of physicists to be the most mathematically consistent, most complete, and most intellectually honest interpretation of quantum mechanics anyone has ever proposed. Some of the most respected physicists alive call it the only interpretation that actually takes the mathematics seriously. Quantum computers are being built on foundations that the many worlds framework explains most naturally. Cosmologists who think about the quantum state of the entire universe find that many worlds is essentially forced upon you. What was once laughed at as science fiction is now a live option in the most serious conversations in theoretical physics. The theory every physicist laughed at turned out to be the only one that works. By the end of tonight, you're going to understand what quantum mechanics actually says and why it created a crisis that physics could not solve for decades. You're going to understand who Hugh Everett was, his brilliance, his stubbornness, his tragedy, and the strange life he built after science rejected him. You're going to understand what the many worlds interpretation actually says, explained simply enough that it will stay with you. You're going to understand why it was rejected so completely and for so long. And you're going to understand why, in 2206, the man who was laughed at is looking more and more like the man who was right all along. Before we go any further, if you find yourself drawn to exactly this kind of thinking, the slow, deep, late-night exploration of ideas that actually matter, then you're exactly who this channel is for. Hit like, subscribe to Calm Theory for Sleep, and help us reach more people like you who need this kind of content in their lives. It takes about 3 seconds, and it makes an enormous difference. Now let us begin. There is a particular kind of suffering reserved for people who are correct before their time. It is different from the suffering of being wrong. When you are wrong, the world pushes back, and the pushback is information. It tells you something. It guides you toward truth. The correction hurts, but it has a purpose. When you are correct before your time, the pushback is noise. The world pushes back not because you are wrong, but because you are inconvenient. Because what you are saying requires too much to change too fast. Because the people who would need to admit error are the most powerful people in the room, and powerful people do not admit error easily. Because the culture of a field is a slow, heavy thing, and individual clarity cannot move it quickly. The pushback feels, from the inside, exactly like being wrong, the same rejection, the same dismissal, the same professional isolation, but it has a completely different meaning. And you will never know, in the moment, which kind you are experiencing. Hugh Everett III spent most of his adult life not knowing. He believed, privately, stubbornly and consistently, that he was right. He said so in letters, in conversations, to his wife and to the occasional colleague who knew about his physics work. He said the world would eventually come around. He was right about that too. He just didn't live long enough to see it. The mathematics, meanwhile, did not require his presence to be true. It was generating the same predictions it had always generated, consistent with every experiment ever performed, waiting for the world to come back and ask it the right questions. The world eventually did, but Everett wasn't there. Tonight is his story. It is also the story of one of the deepest questions in physics. What does it mean for something to happen? When a quantum system exists in a superposition of possible states and a measurement is made, and you get one result rather than another, what actually occurred? Where did the other possibilities go? Did they go anywhere at all? Or are they still here, in some form we have not adequately described? Everett's answer was, they are still here, all of them, always. The universe does not choose. It keeps everything. This is not mysticism. This is what the mathematics says when you refuse to add extra rules that tell it to stop. This is the theory every physicist laughed at. And as you lie here tonight, in the quiet, in the dark, in the particular branch of reality that contains you at this specific moment, consider what it means if he was right. You are here, in this branch, following this path. But the mathematics carries all the other paths too. Every version of every choice you have ever made. Every quantum event that went one way in your experience, and another way somewhere else, in another branch you will never visit, and can never detect. The universe is not a story with one ending. It is every possible ending, running simultaneously forever. Hugh Everett was the first person to say that clearly, and it cost him everything. Let us go back to where it started, to the problem that physics could not solve. The problem that a 25-year-old, over a glass of sherry at a graduate student party, thought he had finally cracked. To understand why Everett's theory was so radical, and why it was so necessary, you need to understand the problem it was solving. And to understand the problem, you need to understand what quantum mechanics actually says about the physical world, and why what it says creates a philosophical crisis that the field has never fully resolved. Quantum mechanics is the most precisely tested theory in the history of science. Its predictions have been verified to extraordinary accuracy, sometimes to 10 or 11 decimal places. It is not an approximation. It is not a limited domain theory that breaks down under careful scrutiny. It underlies every transistor in every computer you have ever used, every laser in every operating room, every MRI machine in every hospital, every LED in every screen you have ever looked at. Modern technological civilization is built on quantum mechanics. There is no experimental result that has ever contradicted it. And yet, for most of the 20th century, nobody agreed on what it actually meant. Not what it predicted, everyone agreed on the predictions. What it meant. What the mathematics was actually describing. Whether it was describing reality at all, or merely providing a useful calculation tool. This is an unusual situation in science. We do not normally build the foundations of entire industries on theories whose meaning is under fundamental dispute. But quantum mechanics is unusual. It is the most successful theory ever created, and it is also the most philosophically contested. The contest has been going on for nearly a century, and it has not been resolved. The crisis is best illustrated with the simplest possible quantum experiment. You have a barrier with two narrow slits cut into it. You fire electrons at the barrier, one at a time. Each electron passes through the barrier and lands on a detection screen behind it, leaving a mark where it hit. If electrons were simply particles, tiny objects with definite positions and velocities, like miniature billiard balls, you would expect each electron to go through either the left slit or the right slit. And on the screen behind you would get two clusters of marks, one behind each slit. That is what bullets do. That is what any classical particle does. But that is not what happens. What you get instead is an interference pattern a series of alternating bright and dark bands spread across the entire screen, like the pattern you get when two sets of water waves overlap and interfere with each other. Peaks meeting peaks reinforce. Peaks meeting troughs cancel out. The result is a complex striped pattern with many bands, not two. This is a wave pattern, not a particle pattern. But wait, electrons are particles. They hit the screen at single points. Each individual electron leaves a single dot when it lands. So how does a long sequence of individual particle impacts produce a wave pattern? The answer that quantum mechanics gives is this. Each electron, before it is detected, spreads through space like a wave. It passes through both slits simultaneously. The part of its wave function that went through the left slit and the part that went through the right slit interfere with each other on the way to the detection screen, constructively in some places and destructively in others, producing the interference pattern. The electron is in a superposition of going through left and going through right at the same time, both simultaneously until the moment it is detected, at which point it manifests at a single point with a probability that matches the interference pattern. Now comes the part that broke physics. What if you put a detector at one of the slits, a gentle detector, something designed to barely disturb the electron that simply records which slit the electron passed through? You run the experiment again. The interference pattern disappears completely. The moment any physical record of which slit the electron passed through exists anywhere in the universe, regardless of whether you ever look at that record, regardless of whether any human being ever learns the result, the interference is gone. The electron stops behaving like a wave spread across both paths. It goes through one slit or the other. You get two stripes on the screen. Classical behavior. No interference. The physical existence of information about the path changed the physical outcome of the experiment. Not the act of a human looking at the information. Not the involvement of consciousness. Simply the physical existence of a record, somewhere in the universe, of which path was taken. That is enough. The interference vanishes. This is the quantum measurement problem. It is not a technical glitch. It is not a detail to be tidied up by the next generation of experiments. It is a fundamental, gaping philosophical crisis sitting at the center of the most successful physical theory ever created. Erwin Schrödinger crystallized the crisis into an image that became famous and is worth understanding properly. A cat is placed in a sealed box. Inside the box is a single radioactive atom, connected to a detector, connected to a mechanism that will release poison if the atom decays. The atom has a 50% probability of decaying in 1 hour. After 1 hour, what is the state of the cat? Quantum mechanics gives a precise answer. The atom is in a superposition of decayed and not decayed. Following the Schrödinger equation, the fundamental equation that governs how quantum states evolve, the detector is in a superposition of triggered and not triggered. The mechanism is in a superposition of activated and inactive. And the cat, if quantum mechanics applies to macroscopic objects just as it applies to subatomic ones, is in a superposition of alive and dead, both states simultaneously, until you open the box and look. Schrödinger intended this as a demonstration of absurdity, a proof that something was wrong with how physicists were thinking about quantum mechanics. Cats cannot be simultaneously alive and dead. Therefore, the interpretation that leads to this conclusion needs to be corrected. The dominant answer, the one that Niels Bohr and Werner Heisenberg had developed in Copenhagen in the late 1920s, the one taught in every physics textbook in the world, addressed this by drawing a sharp line between the quantum world and the classical world. The quantum formalism in Copenhagen's framework is a tool for predicting the outcomes of measurements. The wave function is not a description of physical reality. It is a mathematical object encoding our probabilistic knowledge about a system. When a measurement is made, when a classical measuring device interacts with a quantum system, the wave function collapses instantaneously to the measured value. The superposition ends. One definite outcome results. The cat is alive or dead after the measurement, not before. Bohr's philosophical position stated bluntly, stop asking what is happening to the cat between measurements. Quantum mechanics gives you the probabilities of outcomes. Use it to calculate outcomes. Ask no further questions about the underlying reality. This attitude was sometimes summarized as, shut up and calculate, a phrase coined by David Mermin to describe, not endorse, the approach. It was enormously productive. Everything that makes modern technology possible was built on this pragmatic foundation. But Copenhagen is philosophically broken in ways that become impossible to ignore the more seriously you apply the theory. It requires two fundamentally different rules for how physical systems evolve. First, quantum systems obey the Schrödinger equation, deterministic, continuous, reversible evolution. Second, when a measurement is made, the Schrödinger equation is set aside, and the wave function collapses instantly, randomly, and irreversibly according to the Bohr rule for probabilities. Two rules, different in kind, different in character, and no specification of when the first stops applying and the second begins. This is what Heisenberg called the cut, the boundary between quantum and classical, and nobody has ever been able to say where it is. Eugene Wigner, a Nobel laureate and one of the most rigorous mathematical physicists of the 20th century, sharpened the problem into what is now called Wigner's friend. Suppose a physicist inside a sealed laboratory performs a quantum measurement. Inside the lab, the measurement has happened. The physicist has a definite result. But from outside the sealed lab, before you open it, the physicist is a physical system too. The physicist's body is made of atoms. Atoms obey quantum mechanics. So from outside, applying quantum mechanics consistently, the physicist is in a superposition of having measured outcome A and having measured outcome B. But that cannot be. The physicist inside has a definite result. How can the physicist inside have a definite experience while the physicist outside sees a superposition? Copenhagen has no coherent answer to this. Some versions of Copenhagen try to invoke consciousness as the thing that collapses the wave function. But this creates a new and worse problem. What is consciousness? At what level of biological complexity does it begin? Can an insect collapse a wave function? Can a simple computer? The invocation of consciousness is not a solution. It is a substitution of one mystery for another. By the mid-1950s, the measurement problem was a wound at the center of physics that was kept carefully bandaged. You could do calculations. You could build devices. You could win Nobel Prizes. But if you asked what quantum mechanics actually meant, what was happening in the physical world between measurements, you had no honest answer. The field had learned, under Bohr's influence, not to ask. One graduate student in Princeton had not yet learned to stop asking. Hugh Everett III was born on November 11, 1930, in Washington, D.C. His father was a lieutenant colonel in the United States Army. The family was not warm. The parents divorced when Hugh was young, and he was raised primarily by his mother through a series of houses around the Washington area. The elder Hugh Everett was present enough to cast a long shadow, but absent enough to leave a substantial gap. This pattern, the brilliant, self-contained man who inhabited physical spaces without inhabiting the relationships inside them, would repeat in the next generation with painful fidelity. From the earliest age, it was clear that something unusual was happening in Hugh's mind. He read voraciously, and across everything: science, mathematics, philosophy, history, military strategy. He had the kind of intellectual appetite that makes teachers simultaneously proud and uncomfortable, because it is unsatisfiable by any ordinary curriculum and constantly outpacing what can be offered. He absorbed material faster than it could be presented. He saw implications that the person teaching him had not considered. He asked questions that were precisely the questions you weren't supposed to ask yet, or the questions that nobody in the room had thought to ask at all. He was not popular in the conventional social sense. He was the kind of child who found the interior of his own mind more reliable and more interesting than most social situations. Not because he was incapable of connection, he was capable of it, and capable of warmth when he felt it, but because the connection available inside a genuinely difficult problem was more consistent and more satisfying than the connection available in most human interactions. This preference too would persist. When Hugh was 12 years old, he wrote a letter to Albert Einstein. This fact deserves to sit for a moment. Writing to Einstein at 12 is not the behavior of a child who has calibrated what is socially appropriate. It is the behavior of a child who has not yet learned what is presumptuous, or who has learned it and found the concept insufficiently compelling. He wrote to Einstein because Einstein was the person who had thought most deeply about the questions that interested him. The letter asked about the nature of causation from a logical standpoint. If everything has a cause, what caused the first cause? A cosmological question approached from the angle of mathematical logic rather than theology. Einstein wrote back, Albert Einstein, at 72 years old in the last years of his life, receiving correspondence from across the world from heads of state, from distinguished scientists, from philosophers and theologians and confused members of the public, wrote back to a 12-year-old in Washington because the question was interesting enough to warrant a reply. He did not condescend. He engaged with the question directly. He pointed the boy toward the distinction between logical necessity and physical necessity. The exchange was brief, but it tells you something about both men, about Einstein's generosity of attention, and about the quality of the mind that attracted it. Everett attended Catholic University of America for his undergraduate degree, a somewhat incongruous institution for a young man who was, by that point, a committed atheist. But the physics program was solid, and it was convenient. He started in physics, migrated increasingly toward mathematics. Mathematics was to him the cleanest possible language. A proof was either right or wrong. You could not negotiate with it. There was no requirement to defer to authority, to acknowledge the consensus, to soften your conclusion because it made someone uncomfortable. The logic was what the logic was, and it did not care who you were. He graduated and was accepted in 1953 to the graduate physics program at Princeton University. Princeton's physics department in 1953 was what it sounds like, among the finest collections of working physicists in the world. Einstein had been at the Institute for Advanced Study in Princeton until his death in April 1955, during Everett's first years. John von Neumann, who had placed quantum mechanics on a rigorous mathematical foundation in his 1932 treatise, had been there. Robert Oppenheimer, who had directed the Manhattan Project, was at the Institute. Eugene Wigner, who would formulate the thought experiment that sharpened the measurement problem into its most precise form, was in the physics department. And John Archibald Wheeler, who would become Everett's thesis advisor, was there working, thinking, teaching, willing to follow an idea into territory most physicists found uncomfortable. Wheeler was exactly the right person for Everett at exactly the right time. John Archibald Wheeler was one of the most creatively rangy theoretical physicists of the 20th century. He had worked with Niels Bohr in 1939 on the theory of nuclear fission. He had supervised Richard Feynman's doctoral thesis. He would later coin the term black hole in 1967, and the term wormhole shortly after. He occupied every important intersection in mid-century theoretical physics and crossed between them freely, because he did not believe physics had lanes. Every deep question was connected to every other deep question, and the job was to find the connections. Wheeler was not a Copenhagenist in the complacent sense. He deeply respected Bohr. Bohr had been his collaborator, his mentor, in certain ways, a figure of genuine authority in his intellectual life. But Wheeler held his respect and his open questions simultaneously. He believed the foundations of quantum mechanics were genuinely unresolved. He thought the role of the observer, the nature of the wave function, the meaning of measurement, these were real questions that physics had deferred rather than answered. For a graduate student who wanted to think seriously about the foundations, Wheeler was a gift. A different advisor, one who believed Copenhagen had settled all the meaningful questions and that foundations work was confused philosophy dressed up as physics would have redirected Everett toward. Something more conventional. Wheeler did not redirect. He listened. The story of how Everett first conceived of what would become the many worlds interpretation is told in several versions, with details varying depending on the source. The version most consistently reported involves a gathering of graduate students, a party, or a late evening conversation in 1954 or 1955, with too much sherry and the kind of intellectual freedom that comes when graduate students stop performing and start thinking. Everett was in conversation with fellow students about quantum mechanics, about the double-slit experiment, about Schrödinger's cat, about the measurement problem and why the standard answer was unsatisfying. And Everett asked the question that physics had learned not to ask. Not, how does the wave function collapse? Not, when does measurement happen? But, what if it doesn't collapse? What if the Schrödinger equation is simply true, applied without exception to every physical system, including the measuring device, including the physicist, including everything, and we follow the mathematics wherever it leads, without adding any special rules to make the conclusions comfortable? If the Schrödinger equation governs everything always, then when a quantum particle in superposition interacts with a measuring device, the measuring device doesn't get a definite result. It enters superposition with the particle. The device, in quantum mechanical terms, is now in a superposition of having measured one outcome and having measured another. When a physicist then observes the device, the physicist doesn't get a definite result either. The physicist enters the superposition. The physicist's brain, the physicist's memory, the physicist's entire environment all become entangled in the growing superposition of all possible outcomes. But physicists do get definite results. Every measurement anyone has ever made came out as a single definite answer. So something must be wrong with this picture. Everett's insight, the insight that arrived over sherry, that he would spend the next 2 years making rigorous, was that nothing was wrong with the picture. From inside any one component of the superposition, the physicist has a definite result. The physicist, who is entangled with the spin-up outcome of the particle, has a complete, consistent, real experience of having measured spin-up. The physicist who is entangled with the spin-down outcome has an equally complete, equally consistent, equally real experience of having measured spin-down. Both branches of the superposition are real. Both physicists are real. Neither can detect the other, because the interaction with the environment, with the air molecules in the room, with the photons bouncing around, with everything in the vicinity, has entangled the branches so thoroughly that they can no longer interfere with each other. They have become, for all practical purposes, separate worlds. The universe did not choose between the two outcomes. It kept both. He went to Wheeler with this. Wheeler listened, thought carefully, and told his student to write it up. It would take 2 years to get it right, and once it was right, almost no one was willing to accept it. Everett began the serious writing of his doctoral thesis in 1955 and continued through 1956. What emerged was one of the most unusual documents ever submitted to a physics department anywhere in the world. Unusual not in its mathematical technique, the mathematics was clean, rigorous, and careful. Unusual in its ambition and in its directness. Most doctoral theses in physics are deliberately narrow. They solve a specific technical problem within an established framework. They demonstrate that a student can work competently within the existing structure of a field, apply known methods to new problems, contribute a well-defined piece to a well-defined puzzle. The contribution is real but bounded. Everett's thesis did not do this. It proposed a complete reconceptualization of the foundations of quantum mechanics. It argued that the standard interpretation, the Copenhagen interpretation, taught in every graduate program in the world, developed and propagated by the most respected physicist alive, was not just philosophically unsatisfying, but structurally unnecessary. That a simpler, more complete, more mathematically consistent account was available. That you could take quantum mechanics completely seriously as a physical theory, apply it without exception, and derive everything you needed without any special rules about measurement, observers, or wave function collapse. The original draft ran to 137 pages. It was dense, precise, and in places bluntly critical of the Copenhagen framework, not with hostility, but with the methodical clarity of someone demonstrating that a set of assumptions was unwarranted. It did not treat Bohr's authority as a reason for intellectual deference. It treated Bohr's arguments as arguments, evaluated them, and found them insufficient. Wheeler read the full draft, with genuine admiration for the work, and genuine concern about its reception. Wheeler understood the physics community in a way that Everett did not, or in a way that Everett understood but found not particularly relevant. The argument was right, or it was wrong. If it was right, the length and the directness was simply honest. Wheeler knew it didn't work that way. The machinery of physics ran through people and institutions, and the editorial processes of prestigious journals. And if Bohr's response was contemptuous, the machinery would grind the thesis into professional invisibility, regardless of its content. Wheeler's strategy was to seek Bohr's engagement, not his endorsement, necessarily, but at least his serious consideration. He wrote to Bohr describing what his student had done. He sent draft material. He eventually arranged for Everett to visit Copenhagen directly. Before the Copenhagen visit, the thesis was published in the Reviews of Modern Physics in 1957, in a special issue on the foundations of quantum mechanics. It was published in a form cut down to roughly a quarter of its original length. Everett's working title had been Wave Mechanics Without Probability, direct, clear, announcing its intention. The published title was Relative State Formulation of Quantum Mechanics, more technical, more hedged, less confrontational. The cuts removed most of the philosophical argument, much of the direct engagement with Copenhagen, and left a compressed, technical presentation of the core mathematical formalism. Bryce DeWitt, then a leading researcher in quantum gravity and general relativity, served as a reviewer for the special issue. He was skeptical. His primary objection was the Born rule, the rule that connects the amplitudes in the wave function to the probabilities of measurement outcomes. If all outcomes happen in different branches of the wave function, DeWitt argued, then probability seems to lose its meaning. Why do we experience outcomes with the specific probabilities the Born rule predicts, if all outcomes are equally real? Everett replied in writing, patiently and precisely. On the question of observers feeling themselves split, he pointed out that no observer would have any experience of branching, because from within any branch, the observer has a completely continuous, uninterrupted, singular experience of a definite outcome. The splitting is a structural fact about the global wave function, a fact about the mathematical object that describes the universe, not a phenomenological event. You cannot feel your wave function branching any more than you can feel the quantum events in your neurons firing. On the Bohr rule, Everett argued that probability weights in his framework were the squared amplitudes of the wave function components, the standard Bohr rule probabilities, and that an observer distributed across many branches would correctly self-locate in branches weighted by those probabilities. The argument was not fully rigorous by the standards that would later be applied, but it was coherent, and it was more than the Copenhagen interpretation had managed to produce, since Copenhagen simply assumed the Bohr rule as an axiom, without deriving it from anything deeper. DeWitt was not fully satisfied, but something in Everett's reply stayed with him. Then came Copenhagen. In 1959, Everett traveled to Copenhagen. He was 28 years old. He had already left academic physics. He had taken a position with the Pentagon's Weapons Systems Evaluation Group in 1956, before his thesis was even published, and was visiting as someone who had proposed a major reformulation of quantum mechanics 2 years earlier and had been essentially ignored since. Wheeler had arranged the visit. It was, in retrospect, a last attempt. It did not go well. Bohr was 83 years old. He was the patriarch of quantum mechanics, the person who had built the entire Copenhagen framework, the man whose authority in the field was so immense that challenging him openly was professionally comparable to heresy. His assistant, R.J. Peterson, was often the person who spoke most directly in these meetings, and Peterson was thoroughly unconvinced of Everett's approach from the beginning. The response from the Copenhagen side was essentially, "You have misunderstood what quantum mechanics is for. Quantum mechanics is a tool for predicting measurement outcomes. It is not a description of an independent physical reality that exists whether or not measurements are made. Your error is treating the wave function as physically real and then showing that this leads to branching. But the wave function was never physically real. That was never what it was." Copenhagen understood this from the beginning. And what you have done is to misread the theory and then criticize the result of your misreading. Everett pushed back. He pressed the question of where the Heisenberg cut was where precisely. Quantum mechanics stopped applying, and classical mechanics took over. He pressed the question of how quantum mechanics was to be applied to the universe as a whole, which had no external observer. He pressed the inconsistency of having one rule for quantum systems and a different rule for measuring devices, when measuring devices were also made of atoms. The conversations went nowhere. Bohr and Peterson were arguing from within a philosophical framework that Everett did not share and could not convince them to abandon in a week of meetings. Two people with fundamentally different foundational commitments talking past each other with great precision. Everett returned to Virginia. He returned to the Pentagon work. He gave no further physics presentations, wrote no further physics papers, engaged in no further public discussions of his theory for the next 18 years. The paper sat in the literature, cited perhaps twice a year, mostly by people who disagreed with it. He had been right. He would remain right. The world would take its time noticing. Before we follow Everett's biography further, we need to stop and understand the theory properly. Because many worlds is frequently described carelessly, and the careless description makes it easy to dismiss as science fiction. The careful description makes it very hard to dismiss at all. Let us start at the beginning. The Schrödinger equation is the heart of quantum mechanics. It describes how the quantum state of any physical system evolves over time. The quantum state is encoded in a mathematical object called the wave function. The wave function does not specify definite values of physical quantities. It specifies a distribution of probability amplitudes over all the possible configurations of the system. It tells you not what the particle is doing, but the full range of what it might do, with specific amplitude associated with each possibility. The Schrödinger equation is completely deterministic. If you know the wave function now, you can calculate exactly what it will be at any future moment. There is no randomness in the evolution of the wave function. It flows forward in time continuously, smoothly, reversibly, according to precise mathematical laws. No choices are being made. No outcomes are being selected. The wave function simply evolves. This is the first rule of quantum mechanics. The wave function evolves according to the Schrödinger equation. Always. The problem arrives when you try to connect this to what we actually observe. When an electron that exists in a superposition of two possible locations, say, going left and going right, encounters a detector, the Schrödinger equation tells us what happens. The electron interacts with the atoms in the detector. The combined system electron plus detector evolves into a superposition of two configurations. One in which the electron went left and the detector registered left, and one in which the electron went right and the detector registered right. If a physicist then looks at the detector, the Schrödinger equation continues to apply. The physicist's eyes, retinas, optic nerves, and brain all interact with the detector. The combined system electron detector physicist evolves into a superposition of physicist saw left and physicist saw right. And if the physicist tells a colleague what they saw, the colleague becomes part of the superposition, and so on. The Schrödinger equation propagates the superposition outward through every physical system that interacts with the original measurement, without limit. Standard quantum mechanics at this point introduces a second rule. When a measurement is made, the wave function collapses. The superposition ends. One outcome is selected. The random selection follows the Born rule, which says the probability of each outcome equals the squared amplitude of the corresponding component in the wave function. So if the went left component has amplitude 1 over root 2, the probability of getting the left result is 1/2. Everett's proposal: eliminate the second rule. There is no collapse. There is only the first rule. The Schrödinger equation applies always to everything, without exception. What happens then? The physicist who interacted with the detector is now in a genuine physical superposition. But crucially, something called decoherence occurs immediately and essentially instantaneously. Decoherence is the process by which quantum superpositions lose their ability to interfere with each other through interaction with a larger environment. An isolated quantum system can be in a superposition whose components interfere with each other. This is what produces the interference pattern in the double-slit experiment. But a macroscopic object, like a detector, is not isolated. It is in constant contact with air molecules, thermal radiation, photons from the lights in the room, the vibrations of the table, and countless other environmental degrees of freedom. Each of these interactions entangles the detector's state with the environment. The superposition of the detector does not go away, it spreads. It spreads into the environment, becoming entangled with billions and billions of environmental degrees of freedom. Once that spreading has occurred, the different components of the superposition, the detector reads left component and the detector reads right component, can no longer interact with each other. The environmental entanglement has made them effectively orthogonal in the enormous space of all possible quantum states. They cannot overlap. They cannot interfere. For all practical purposes and for most theoretical purposes, They are completely separate. For a macroscopic object in a normal environment, this decoherence happens on timescales so short that no human technology can observe the superposition before it decoheres. We are talking about timescales of 10 to the minus 23rd seconds or shorter. For all practical purposes, instantaneous. The result is that the different outcome components of the universal wave function become, after decoherence, completely separate branches. The physicist, in the left branch, has a complete, consistent, classical-looking experience of a world in which the electron went left. The physicist in the right branch has an equally complete, equally consistent, equally classical-looking experience of a world in which the electron went right. Neither branch can detect the other. They cannot interact. They cannot send signals to each other. The physics of decoherence has separated them as thoroughly as if they were in completely different universes. In a sense, they are. In the sense that matters for physical experience, they are completely separate worlds. But they are not separate universes in the science fiction sense of bubble universes floating in some higher dimensional space. They are branches of a single quantum state, the universal wave function, that has become so entangled with its environment that different components no longer interact. They are not located in different places. They are not physically separate in any spatial sense. They are different components of the same mathematical object, differentiated by their quantum state rather than their location. This is what many worlds means, not many spatial universes. Many branches of the universal wave function, each of which constitutes a complete, consistent, classical-seeming reality for the observers within it. The branching is happening constantly. At every quantum event, everywhere in the universe, at a rate utterly beyond any ordinary description. Every radioactive decay that could go either way. Every photon that could be reflected or transmitted. Every electron in every chemical bond in every molecule. Every ion channel opening in every synapse in every nervous system. Branching. Ceaselessly. Silently. Without any observer being able to feel it. What does this mean for you? Right now, reading or listening to these words, quantum events are occurring in your brain. The biochemistry of your neurons has quantum components. Ion channels open probabilistically. Electrons transfer in molecular reactions. The vast majority of these quantum events have no macroscopic consequence. The branches they create are nearly identical, differing by amounts too small to affect anything at the scale of thoughts or actions. But they are branching. You are branching. In total silence, with no sensation, continuously. Now comes the most challenging part. If all outcomes happen, what does probability mean? This is the Born rule problem, and it is the most serious technical challenge the many worlds interpretation faces. In standard quantum mechanics, the Born rule simply says, the probability of a given measurement outcome equals the square of the modulus of the corresponding wave function amplitude. In many worlds, all outcomes happen. There is no selection. So what does probability mean, and why should you expect to observe outcomes in proportion to their squared amplitudes? Everett addressed this in his original thesis. His argument was that probability in many worlds was the measure the weight of the branches. Different branches have different amplitudes, and the squared amplitude gives the natural measure over the space of branches. An observer should expect to find themselves in branches weighted proportionally to their squared amplitudes. Because that is what the mathematics of the wave function implies when you ask about the statistics of self-location across many branches. This argument was made mathematically rigorous decades later by David Wallace using decision theory. Wallace showed that a rational agent who believed in many worlds and wanted to make the best possible decisions under uncertainty about which branch they would find themselves in. should assign betting probabilities exactly according to the Bohr rule. The Bohr rule in many worlds is not a postulate, it follows from rationality applied to the structure of the wave function. The other interpretations simply assume it. Many worlds, at least in Wallace's formulation, derives it. The derivation remains philosophically controversial. Some critics find it circular. Some find it question-begging. The debate is ongoing, and it is a real debate among serious philosophers and physicists. But it is a mathematically serious attempt to do something no other interpretation has managed, to explain why the Bohr rule is true rather than simply assuming that it is. This is what Many Worlds actually says. One equation, applied to everything, no exceptions, no collapse. Branching instead of selecting. The universe keeping every outcome, forever, in the structure of the wave function. It is the simplest possible response to the measurement problem. It is what you get when you take quantum mechanics seriously as a complete description of reality and refuse to add anything extra to make the conclusions comfortable. It is what a 25-year-old arrived at over a glass of sherry in 1954. The rejection of Everett's Many Worlds interpretation was not accidental. It was not a simple failure of imagination. It had causes, sociological causes, philosophical causes, and some legitimate technical causes, and understanding them is important for understanding both Everett's story and the way science actually works when it is working imperfectly. Niels Bohr had won the Nobel Prize in Physics in 1922. By 1957, he had been the dominant figure in quantum theory for 30 years. He had been present at the creation of the field, had debated Einstein across a decade at the Solvay conferences, had built the Copenhagen Institute, trained a generation of physicists, and exported the Copenhagen interpretation to every physics department in the world through those students. He was not merely respected, he was the living embodiment of quantum mechanics as a human achievement. His authority was not just intellectual, it was institutional, cultural, and generational. Challenging Bohr in 1957 was not like challenging a contemporary whose arguments could be examined on their merits in a room of peers. It was like challenging an institution, a tradition, an orthodoxy that had been productive for 30 years and that the entire field had built upon. Even physicists, who privately harbored doubts about the philosophical coherence of Copenhagen, tended to keep those doubts private, because voicing them meant positioning yourself in opposition to Bohr. And that position, in 1957, was professionally dangerous. The specific technical objections to Many Worlds were not without force, and they deserved to be taken seriously. The first was ontological excess. The Many Worlds interpretation implies a number of real physical branches that is not just large, but incomprehensibly, staggeringly, beyond all human intuition large. Every quantum event, and there are an incomprehensible number of them, occurring everywhere in the universe, at every moment, spawns new branches of reality. The number of branches grows exponentially at rates beyond any description. Why should we believe in all of this? Occam's razor says we should prefer the simpler theory. Many Worlds appears to be the opposite of simple. Everett had an answer, and it was a good one. The simplicity that matters in physics is the simplicity of the theoretical structure, the economy of the laws, not the simplicity of what the laws imply. The Schrödinger equation is one equation with no exceptions. Copenhagen requires two rules with a mysterious and undefined transition between them. In terms of theoretical structure, Many Worlds is simpler. In terms of implied entities, it is more extravagant. Which kind of simplicity you value depends on your philosophical commitments. And in 1957, those commitments were overwhelming on the Copenhagen side. The irony which Everett noted, and which has been noted by many since, is that Copenhagen is actually the theory with more ingredients. Copenhagen adds the collapse postulate, adds the concept of measurement as a primitive term, adds the distinction between quantum and classical systems, and adds the Bohr rule as a separate axiom. Many worlds adds none of these things. It takes quantum mechanics at face value and derives consequences. The charge of excessive complexity, leveled at many worlds by its critics, applies with equal or greater force to its accusers. The second objection was the Bohr rule problem. If all outcomes happen, probability seems to lose its meaning. This was a genuine weakness in Everett's 1957 presentation. His argument for recovering the Bohr rule was suggestive but not rigorous by the standards that would later be applied. This would not be adequately addressed until David Wallace's decision-theoretic derivation decades later. In 1957, the weakness was real, and pointing to it was fair. The third objection was untestability. The other branches of the wave function cannot be detected. They leave no observable trace in any experiment we can perform. They are, in principle, inaccessible. What kind of scientific theory proposes entities that are, in principle, unobservable and then calls them real? This objection is weaker than it sounds, and its weakness is important. Electrons, before they are measured, cannot be directly observed. Either we observe only their effects on detectors, which are themselves made of quantum systems. The unobservability of the other branches is precisely the same kind of unobservability as the regions of the universe beyond our cosmological horizon. We cannot see them. They cannot signal us. But there is no logical or physical principle that makes their existence impossible or implausible. The objection from unobservability is an objection from our epistemic limitations, not from the physics. Physics is full of unobservable entities, forces, fields, quantum states themselves that we accept because they explain what we do observe. And then there was the naming. Bryce DeWitt, in his 1967 Physics Today article that began the rehabilitation of Everett's work, called it the many worlds interpretation. Everett had called his framework the relative state formulation, a dry, precise technical name that described exactly what the mathematics was doing. Many worlds was dramatic. It sounded like the title of a science fiction novel. It invited a mental image of bubble universes floating in some higher dimensional void, of science fiction imagery from the pulp magazines of the 1950s. The name made it easy to dismiss the theory without engaging with it, because you could roll your eyes at many worlds and signal, without any mathematical engagement, that you found the whole thing silly. Everett hated the name. He had been careful, in his original formulation, to use exactly the language that would make his work hardest to dismiss on superficial grounds. DeWitt's coinage undid some of that care. John Bell deserves special mention here. Bell was the Irish physicist who proved Bell's theorem in 1964, perhaps the most important result in the foundations of quantum mechanics since the theory was created, demonstrating that quantum mechanics is irreducibly non-local in a precise, testable sense. Bell understood the measurement problem deeply. He was sympathetic to the reality of the problem, skeptical of Copenhagen's resolution of it, and interested in Everett's approach. In private conversations and letters, he was more charitable to many worlds than almost any other physicist of comparable standing. But he never publicly championed it. He had reservations about the Bohr rule derivation. He had concerns about some of the ontological commitments. His private sympathy never converted into the kind of public advocacy that could have moved the professional conversation. Without Bell's public voice, the theory had no one of his stature speaking for it. The sociology of academic physics in 1957 was not configured for the reception of a 26-year-old graduate student's challenge to the dominant framework. You needed senior advocates. You needed institutional backing. You needed the right people in the right rooms to say, out loud, in print, that this was serious work worth taking seriously. Everett had Wheeler, but Wheeler was perpetually cautious, perpetually aware of Bohr's likely response, perpetually pulling the presentation of the idea back from its most confrontational edges. Without more advocates, the theory had no path forward. The paper was published, it was correct, and it disappeared into the literature with barely a sound, like a stone dropped into a very deep well. Hugh Everett left academic physics before his thesis was even published. He accepted a position with the Weapons Systems Evaluation Group in Washington, D.C. in 1956. The Weapons Systems Evaluation Group was a Pentagon-adjacent research organization that performed quantitative analysis of military problems, operations research, game theory, and the mathematical modeling of complex strategic scenarios. It was exactly the kind of work that required a mind capable of holding enormously complex, abstract structures without losing track of their implications, comfortable with probability and strategic logic. I'm interested in the difference between a theoretical problem and a real-world application. Everett was extraordinarily well suited for it. He rose quickly. He was given increasingly complex and sensitive problems. His specialty became the quantitative analysis of nuclear war scenarios, the mathematics of deterrence and mutual assured destruction, of first strike and second strike strategies, of survival probability under different targeting doctrines, of damage assessment models for cities and military installations. This was not abstract work in any final sense. The frameworks and algorithms Everett helped develop contributed to actual policy about how the United States planned to conduct and perhaps survive a nuclear exchange with the Soviet Union. Most of the specific details of his work are classified to this day. The irony of this career path is profound enough to be almost literary. The man who had proposed that every possible quantum event branches into a new version of reality, that the universe never forecloses a possibility, that every outcome is real in some branch, that nothing is ever truly lost, spent his professional working life determinate which branches of human history to terminate. How many nuclear weapons, targeting which cities delivered by which means, would produce what expected outcomes, in what probability distribution? He was, professionally, in the business of deciding which futures to foreclose. In 1964, Everett founded Lambda Corporation, a private defense contracting firm based in Virginia. Lambda provided sophisticated mathematical and quantitative analysis services to government clients, primarily the Department of Defense. Everett ran it until the end of his life. He was, by the standards available to him, professionally successful. Lambda worked. It grew. It paid well. His home life was harder. He had married Nancy Gore in 1956, the year he left physics. They had 2 children, a son, Mark, born in 1963, and a daughter, Elizabeth, born in 1956. Mark Everett grew up to become E, the founder and sole consistent member of the band Eels, one of the more emotionally distinctive and critically respected alternative rock bands of the past 3 decades. His music has returned, across album after album, to themes of grief, loss, family silence, the difficulty of connection, and the presence of absence. You do not need much biographical knowledge to understand where those themes came from. Mark has described his father in his memoir and in interviews over the years. The description is consistent across sources. A stranger who happened to live in the same house. Not cruel by all accounts. Not actively harmful. Simply absent in the way that some people are absent while physically present, a man for whom the interior life of calculation and analysis was so much more vivid and real than the social interior of a family, that the family lived in a kind of permanent secondary existence. Hugh Everett worked. He came home, he went to his study, he drank throughout his adult life, consistently and heavily. He smoked. He was significantly overweight. He communicated with his wife and children occasionally, briefly, when something occurred to him that seemed worth saying, and otherwise not. He was not a father in any active, engaged sense. He was a physical presence in a house that his family shared with someone they barely knew. He occasionally checked whether his 1957 paper had been cited. The answer, year after year through the 1960s and into the early 1970s, was barely. 1 or 2 citations per year, mostly critical, mostly brief acknowledgments that the interpretation existed before explaining why it was wrong or confused. The paper existed in the physics literature the way a message in a bottle exists in the ocean, technically present, practically invisible. He told his wife, in conversations she remembered afterward, that the world would eventually come around. Not with bitterness, apparently, with a kind of flat, untroubled certainty. The mathematics was what it was. The physics said what the physics said. The rest of the field would catch up when it was ready. He was right. The timing was just wrong. In 1967, Bryce DeWitt published an article in Physics Today titled Quantum Mechanics and Reality. DeWitt had changed his mind. His decade of work on quantum gravity, on the attempt to reconcile general relativity with quantum mechanics, on the project of writing down a wave function for the universe as a whole, had brought him, slowly and reluctantly, to the conclusion that many worlds was not one interpretation among several equals. When you tried to apply quantum mechanics to the entire universe, Copenhagen collapsed immediately, because Copenhagen required an external classical measuring apparatus to give the quantum formalism its meaning, and the universe had no outside. There was no external classical domain when the domain you were describing was everything. Many worlds didn't require one. Many worlds was, for quantum cosmology, not one option, but the only option that wasn't obviously incoherent. DeWitt wrote the article. He coined the phrase, many worlds. He sent a copy to Everett at Lambda Corporation in Virginia. Everett replied. He was surprised and genuinely pleased. He was also characteristically precise about the places where DeWitt's presentation diverged from his original formulation. A correspondence began. In 1973, DeWitt and his student Neil Graham published an anthology, The Many Worlds Interpretation of Quantum Mechanics. The anthology included Everett's complete original 137-page thesis, the full version that Wheeler had forced him to cut before. Publication, the complete argument that the physics community had never seen in its entirety. For the first time, the full scope and depth of what Everett had actually written in 1956 was available to anyone who wanted to read it. Letters began arriving at Lambda Corporation's address in Virginia, from graduate students who had read the anthology, from physicists who found the full argument more compelling than the trimmed, published version, from philosophers of science who thought the ontological questions were serious. Everett replied to the ones that raised genuine mathematical or physical questions. His replies were patient with honest confusion, brief with the kind of confusion that was simply carelessness, and precise throughout. In 1977, a conference on the foundations of quantum mechanics was held at the University of Texas at Austin. Everett was invited to give a talk. He had not given a physics presentation in more than 20 years. He came. The room was different from the room he had faced in 1957. The generation formed under Bohr's direct influence was older or gone. The physicists in the audience had grown up with the measurement problem as an acknowledged difficulty rather than a solved one. They were curious, not hostile. They wanted to understand. Everett talked for hours. He answered questions for hours. The questions were good, precise questions about decoherence, about the Bohr rule, about the ontological status of branches, about the relationship to quantum cosmology. He answered them with the same systematic calm he brought to every hard problem. Afterward, students came forward with copies of the anthology and asked him to sign them. He was 47 years old. He had 4 more years to live. The drinking had never stopped. The smoking had never stopped. He was overweight and had been for many years. He had, by all accounts, made no particular effort to look after his physical health, ever, at any point in his adult life. His body was the container for the calculation, and the container had been treated accordingly. On July 19, 1982, in his home office in McLean, Virginia, Hugh Everett III died of a heart attack at the age of 51. His wife, Nancy, found him. He had asked, in various forms over the years, that his ashes not be preserved, that they be discarded, thrown in the trash. He said, with his characteristic flatness about matters that others found laden with significance, that he didn't care what happened to his body after he was gone. Wherever he was going, he wouldn't need it. His daughter Elizabeth honored the request. Elizabeth Everett struggled in the years after her father's death. She inherited, by all accounts, both his intellectual intensity and his difficulty with the ordinary requirements of daily life. In 1996, at the age of 39, she died by suicide. She left a note saying she was going to find her father in a parallel universe. In every branch of the wave function, the mathematics was right. The family paid the price in each one, differently. Vindication in physics does not arrive in a single moment. There is no ceremony, no correction of the record press conference, no official committee that convenes to announce that a previously dismissed idea has been found sound. What happens instead is a slow, uneven, frequently grudging shift in professional conversation. Papers begin accumulating citations. More researchers feel safe choosing the topic as a direction. Senior figures allow themselves to say, in public, things they had previously said only in private. The idea migrates from fringe to periphery to contested minority to serious option. And the transition at each stage is poorly defined and visible only in retrospect. The vindication of many worlds has followed this pattern over the past 50 years. Imperfectly and incompletely, but unmistakably. DeWitt's 1973 anthology was the first real inflection point. Putting Everett's complete argument in front of the physics community changed the texture of the professional conversation. People who had dismissed many worlds on the basis of the heavily trimmed 1957 published paper, or on the basis of DeWitt's dramatic name and its science fiction connotations, now had to engage with a full 137-page mathematical argument. Some of them found, on engagement, that it was more substantial than they had assumed. The second major step came from an unexpected direction: quantum computing. In 1985, David Deutsch, then at Oxford, now widely recognized as one of the most important theoretical physicists of the late 20th and early 21st centuries, a key architect of the theory of quantum computation, published a landmark paper in the Proceedings of the Royal Society. The paper introduced the concept of a universal quantum computer and argued that such a machine could solve problems that no classical computer could solve efficiently. Deutsch's paper was explicitly grounded in many worlds. He argued that the power of quantum computation was not mysterious in the many worlds framework. A quantum computer running a calculation runs it on all inputs simultaneously, in superposition across different branches of the wave function. The quantum parallelism, the apparent simultaneous processing of many possibilities that gives quantum computers their power, is, in Deutsch's view, literally the computation happening in different branches of the universal wave function. The answer extracted at the end of the computation is the result of quantum interference between those branches, which concentrates information from all of them into a single measurable outcome. Deutsch was explicit about the implication. Quantum computers were the strongest available empirical evidence for the reality of the many worlds interpretation, because quantum computation was only comprehensible if the parallel branches were real. If many worlds were false, if only one branch of the wave function were real, then quantum computing would require an inexplicable mechanism for performing exponentially many computations with a finite physical system. Many worlds provides the mechanism. The branches are real. The computation happens in them. This argument is disputed. Other interpretations have accounts of quantum computation. Pilot wave theory says the guiding wave performs the parallel work. Copenhagen says the predictions come out right, so ask no further questions. But no other interpretation explains quantum computing in an intuitively clear, physically satisfying way. Many worlds does. And quantum computing is not a thought experiment. IBM, Google, and others have built quantum computers with hundreds and now thousands of physical qubits. Quantum advantage over classical algorithms has been demonstrated for specific problem classes. The technology is real. Something is using quantum superposition to perform parallel computation. The debate about what that something is has concrete stakes. Throughout the 1990s and 2000s, Max Tegmark, first at the University of Pennsylvania, later at MIT, became an increasingly visible advocate for many worlds in both technical and public forums. He conducted informal surveys at major physics conferences, asking which interpretation physicists favored. The results, when reported, surprised many commentators. A substantial fraction of respondents in some surveys, approaching 30 to 40%, favored many worlds or versions close to it. Copenhagen remained the plurality choice, particularly among older physicists and experimentalists. But the numbers demonstrated clearly that many worlds was not a marginal view held by a few eccentric theorists. It was a substantial minority position among serious physicists. Sean Carroll, a theoretical physicist with a background in cosmology and quantum gravity, became in the 2010s and 2020s the most publicly prominent champion of many worlds. His 2019 book, Something Deeply Hidden, made the case to a general audience with unusual force and clarity. Carroll's argument went beyond defending many worlds as one reasonable interpretation among several. He argued that it was the correct interpretation, and that all the alternatives were motivated primarily by psychological discomfort with what the mathematics implied, rather than by genuine theoretical reasons. His case in brief: take quantum mechanics seriously as a physical theory. The wave function is real. The Schrödinger equation is true. Apply them consistently to everything, without special cases for measurements or observers or consciousness. What do you get? You get many worlds. Every other interpretation adds something: a collapse mechanism, a preferred basis selected by hand, hidden variables, an observer-dependent reality to avoid the conclusion that the wave function is real, and branches. These additions are not supported by any evidence. They are motivated by the desire to avoid the strangeness of the conclusion. Many worlds accepts the strangeness. That is the price of intellectual honesty. Parallel to this, the decoherence program, which had begun with Dieter Zey's largely ignored 1970 paper on the emergence of classical behavior from quantum mechanics, matured through the work of Wojciech Zurek and others into one of the most precise and well-confirmed areas of modern quantum physics. Decoherence theory explains, in mathematical detail, how quantum superpositions behave in macroscopic systems, how they become effectively classical, why specific physical quantities, position, energy, certain field amplitudes, are the ones that decohere first and fastest, and why the world we observe at ordinary scales looks classical, even though the underlying physics is quantum mechanical. Decoherence theory did not prove many worlds, but it provided the physical mechanism that makes many worlds coherent and specific. It explained why we do not observe quantum superpositions at macroscopic scales, because they decohere into effectively separate branches so quickly that the coherence is unobservable. It addressed the preferred basis problem, the question of which way to decompose the wave function into branches by showing that the preferred basis is determined by the structure of the local environment, not by any arbitrary choice. It made many worlds a concrete, precise, physically grounded proposal, rather than a vague philosophical position. In 2013, at the Quantum Physics and the Nature of Reality conference in Blacksburg, Virginia, a gathering specifically of physicists who worked professionally on the foundations of quantum mechanics, a poll of attendees found that many worlds received plurality support, narrowly ahead of Copenhagen, and information-theoretic approaches. This was the subset of physicists who had thought most carefully about the measurement problem, who had dedicated their professional lives to understanding what quantum mechanics meant. Among them, in plurality, many worlds was the preferred answer. That is a long way from where things stood in 1957. The laughing stopped. The dismissal stopped. The theory that was called meaningless by the most respected physicist of its era is now engaged with seriously, criticized carefully, defended rigorously, and held by physicists of extraordinary caliber as their considered view of the most fundamental physical theory in science. Everett was right in 1957. He was right in 1982, when he died. He was right in 1996, when his daughter wrote about parallel universes in her final note. The rest of physics has been, slowly and at enormous cost in wasted time, catching up. The claim in the title of tonight's video is a strong one, the only one that works. I want to defend it seriously, not rhetorically, by going through the competition honestly and being precise about what each interpretation can and cannot do. There are 5 interpretations of quantum mechanics that are taken seriously by professional physicists today, not equally seriously, and not all by the same physicists. But each has genuine, thoughtful proponents who are not confused and not careless. Let us go through them honestly. Copenhagen, the oldest and the most widely taught. In its pragmatic form, Copenhagen says quantum systems are described by wave functions that evolve according to the Schrödinger equation. When a measurement is made, the wave function collapses to the measured outcome, with probability given by the Bohr rule. The wave function is a calculational tool, not a description of independent physical reality. Questions about what is happening between measurements are either meaningless or beyond the proper scope of physics. Copenhagen works. It has worked for nearly a century. It gives the right experimental predictions for every experiment ever performed. You can build a career, win a Nobel Prize, and design revolutionary technology using Copenhagen without ever encountering a contradiction. But Copenhagen fails as a foundational account of physics in ways that become increasingly critical as you apply it in deeper and broader contexts. It requires 2 fundamentally different rules for how physical systems evolve: the Schrödinger equation and the collapse postulate, with no specification of when the first stops applying and the second begins. The Heisenberg cut between quantum and classical is invoked constantly but never located. When pressed on where it is, the Copenhagen answer is essentially that asking this question is a category error. But asking this question is a category error is not a physical answer. It is a refusal to provide one. It invokes measurement as a fundamental concept without defining it. What counts as a measurement? An interaction with a detector? An interaction with any macroscopic object? Only an interaction observed by a conscious being? The word is used throughout the formalism without ever receiving a precise physical meaning. For a theory that claims to be about what can be measured, this is a serious lacuna. It breaks down irreparably when applied to the universe as a whole. Quantum cosmology, the attempt to apply quantum mechanics to the universe as a complete quantum system, which the theory's universality seems to require, needs a wave function for the universe. Copenhagen requires an external classical observer to give that wave function its meaning. The universe has no outside. Copenhagen, applied to cosmology consistently, produces an incoherence that cannot be patched. This is not a philosophical worry about foundations that practicing physicists can safely ignore. It is a technical breakdown in exactly the regime where modern theoretical physics needs quantum mechanics to work. Pilot wave theory, developed by de Broglie in the 1920s and made rigorous by David Bohm in 1952. In pilot wave theory, particles always have definite positions. They are real, localized objects at every moment. The wave function is also real, a physical field that guides the particle's motion through configuration space. The particle follows the guidance equation, which is determined by the wave function. The wave function evolves according to the Schrödinger equation without collapse. Pilot wave reproduces all quantum mechanical predictions exactly. It is a genuine, fully worked out alternative. It is explicitly realistic and explicitly deterministic. The apparent randomness of quantum measurements comes from our ignorance of the particle's initial position. If you knew the exact initial positions of all particles, you could predict every outcome exactly. The serious problem with pilot wave is non-locality. The wave function of a many-particle system lives in configuration space, a space with 3 dimensions for each particle in the system. For a system of 2 particles, this is a 6-dimensional space. For a system of 1 billion particles, this is a 3 billion dimensional space. The guidance equation tells each particle where to go, based on the wave function in this configuration space, which depends on the positions of all other particles simultaneously. Change the position of one particle, and the guidance for every other particle in the universe changes instantaneously. This non-locality is carefully structured so it cannot be used to send signals faster than light. But it is real, structural, and deep. Building a fully Lorentz invariant version of pilot wave theory, a version consistent with special relativity, is a significant and not fully solved technical challenge. For physicists whose work requires both quantum mechanics and special relativity, this is a real problem. There is also an aesthetic and ontological issue. Pilot wave theory keeps all the branches of the wave function. It is as ontologically extravagant as many worlds in this respect. But it adds particles that ride only one branch. The other branches are real in the wave function, but empty of particles. They exist as physical structures in configuration space, with no particles in them. Pilot wave trades the many observers of many worlds for many empty branches, plus one set of particles. It is unclear that this represents genuine simplification. Relational quantum mechanics, developed by Carlo Rovelli in 1996. In relational QM, quantum states are not absolute properties of systems. Every quantum state is a state relative to some observer or reference system. There is no observer-independent quantum state of anything. What one observer knows about a system and what another knows can legitimately differ, and both descriptions are correct for their respective frames. This dissolves the Wigner's friend paradox by declaring that the conflict between the friend's description from inside the box and Wigner's description from outside is not a contradiction. They simply have different, valid, relational descriptions of the same system from different reference frames. Many physicists find relational QM philosophically unsatisfying because it abandons observer-independent physical reality. For most physicists, science describes a world that exists independently of whether anyone is looking at it. Relational QM says there is no such world, only networks of relational facts between observers and systems. This is coherent, but it requires abandoning a commitment to scientific realism that most physicists hold implicitly and deeply. Recent work by Frauchiger and Renner has suggested that relational QM may produce logical contradictions in extended Wigner's friend scenarios, involving observers modeling each other. The debate is ongoing. Cubism, quantum Bayesianism, developed by Christopher Fuchs and Rüdiger Schack. In cubism, the wave function is not a physical object at all. It is an agent's personal probability assignment over possible measurement outcomes, a tool for calibrating beliefs, not a description of the world. Quantum mechanics, in this view, is a normative theory telling rational agents how to update their beliefs. It says nothing directly about reality independent of agents. Cubism escapes the measurement problem by dissolving it. If quantum mechanics is about agent beliefs rather than physical reality, then there is no paradox about wave function collapse, because the collapse is just a belief update when new information arrives. Perfectly ordinary Bayesian updating. No mystery. The price is substantial. If quantum mechanics says nothing about reality independent of agents, physics has abandoned its traditional project of describing the world. Most physicists consider this price too high. Science is not only about our knowledge of reality, it is about reality itself. Objective collapse theories, GRW, CSL, the Penrose interpretation, and related proposals. These theories modify the Schrödinger equation by adding a physical mechanism that causes wave function collapse to occur spontaneously and randomly, with a rate calibrated so that quantum superpositions survive long enough to show quantum behavior for microscopic systems, but collapse fast enough to be unobservable for macroscopic ones. Objective collapse theories are scientifically distinctive and admirable in a specific way. They propose new physics that differs in principle from standard quantum mechanics. They make predictions that could in principle be distinguished from the predictions of unmodified quantum mechanics. If quantum gravity causes collapse at the Planck scale, as Penrose's version proposes, then sufficiently sensitive tabletop experiments might detect the collapse mechanism. The problem is that objective collapse theories are modifications of quantum mechanics. They assume the measurement problem is a genuine physical problem, requiring new physics to solve. If many worlds is correct, the measurement problem is not a problem at all. It is a consequence of taking the existing, unmodified, experimentally confirmed quantum mechanics seriously as a complete description of reality. Objective collapse theories add new physics to solve a problem that may not need new physics. Many worlds. Take the Schrödinger equation. Declare it true. Declare it applies to everything. Always, without exception. Make no additions. Introduce no special cases. Invoke no privileged role for measurement, observers, or consciousness. Ask what follows. What follows is branches. Decoherence separating the branches into effectively distinct classical-looking worlds. A derivation of the Born rule, from the structure of the wave function and the rationality of observers distributed across branches. A quantum cosmology without the need for an external observer. A natural account of the power of quantum computation. A single universal law with no exceptions, No hidden variables, no privileged classical domain, no mysteries about where the cut between quantum and classical lies. The cost is the number of branches. But this cost, properly understood, is not obviously greater than the ontological costs already accepted in standard physics. If the universe is spatially infinite, as standard cosmology suggests, it contains infinitely many copies of everything, including you, including every possible configuration of matter. The branching in many worlds does not add to the ontological complexity of an already infinite universe. It is the same infinity, differently arranged. Many worlds is not proven. It is not consensus. The Born rule derivation is contested. The precise definition of branches and the question of when exactly a superposition becomes two branches rather than one is not fully resolved. These are real open problems. But of all the interpretations, many worlds is the one that adds the fewest ingredients to the established, experimentally verified physics. It takes quantum mechanics at face value and accepts the consequences. All the other interpretations add something, add collapse, add hidden variables, add observer dependence, add new physical mechanisms to avoid the consequence. Many worlds refuses to add anything. It takes the equation seriously. That is why it might be the only one that actually works. Hugh Everett III was born on November 11, 1930, in Washington, D.C. He wrote a letter to Einstein when he was 12 and received a reply. He entered Princeton at 22. He conceived of many worlds at 24 or 25, over a glass of sherry at a party for graduate students. He completed his thesis at 26. He was dismissed by Bohr at 28. He spent the next 24 years calculating nuclear strategy. He died at 51. His ashes are in a landfill somewhere in Northern Virginia. That is one summary of his life. Here is another. He looked at the most successful and most philosophically confused theory in all of science. He asked the simplest possible question: what if the equation is just true? He wrote down the answer in mathematical detail. He got it right. He submitted his work to the best physicist department in the world, where the best physicists dismissed it. He was 26 years old when he was right about something that would take the rest of physics 60 more years to begin to accept. Both summaries are about the same man. Both are true. The many worlds interpretation says that in every branch of the wave function where the physics plays out, both are true simultaneously. In the branch where Bohr sat across from Everett in Copenhagen in 1959 and said, "I think I need to understand this more carefully," in that branch, Everett does not leave physics. In that branch, he watches decoherence theory develop in the 1970s and recognizes it as the mathematical completion of his original idea. In that branch, he is in the audience when David Deutsch presents quantum computing in 1985 and understands immediately what it means for his interpretation. In that branch, he reads the surveys showing that plurality support for many worlds has emerged among the physicists most qualified to judge. In that branch, he writes letters and gives lectures and lives to see the laughing stop. In this branch, he does not. In this branch, the man who may have understood the structure of reality more clearly than anyone of his generation died at 51, of preventable causes, without recognition, having spent his working life in a different room entirely. In this branch, his daughter took her own life in 1996, at the age of 39, leaving a note about parallel universes that is heartbreaking in ways that compound with everything you now know about her father. She never saw his vindication either. She barely saw him. This is not a story with a satisfying ending. It is not a story about a man who was rejected and then triumphant. It is a story about a man who was rejected and remained rejected for the entirety of his short life. And then after his death, and his daughter's death, and the ashes in the landfill, the rest of physics came around. The arc of physics does bend toward truth, eventually. But the timescale of that bending is longer than a human life, and sometimes much longer. And yet, the mathematics did not require Everett's presence to be true. The Schrödinger equation was generating correct predictions before Everett was born, and will continue after every person alive today is gone. The branching was happening before Everett proposed it, in the structure of the universal wave function in every quantum event that has ever occurred. The branches were real before Bohr dismissed them. The vindication, in the deepest sense, was always built into the physics. The acknowledgement of the vindication was what took 60 years. But the vindication itself was immediate. Nothing is lost in many worlds, not even the physicist who walked away. The universal wave function carries the quantum history of every system that has ever existed, in every branch where it existed, permanently encoded in the structure of the most fundamental physical object we know. Hugh Everett III, the particular configuration of matter and energy and quantum states that constituted a man who thought clearly about one of the hardest problems in science. That configuration exists in the wave function, in every branch where it was real. Physics does not discard. The wave function does not forget. Tonight, as you lie here, in the quiet and the dark, in the particular branch of the universal wave function that you are in right now, in the specific path through the branching tree that has led you to this exact moment, this exact breath, this exact resting of your body in this particular space, consider what it means to be here. Right now, quantum events are occurring in your neurons. Ion channels are opening probabilistically. Electrons are being transferred in the biochemical machinery of thought and memory, and the slow chemistry of the body approaching sleep. These events have quantum components. They are branching, silently, instantaneously, without any sensation. The version of you that is falling asleep right now is branching into futures. The vast majority of those futures are nearly identical to this one. The classical world is robust to quantum fluctuations at the scale of neurons and choices and lives. But at the quantum level, the branching continues. Every moment and every branch is real. You are not one person living one life. You are one path through an incomprehensibly large tree. The tree contains every version of you, versions that diverged this morning, versions that diverged years ago, versions barely distinguishable from you, and versions very different, all of them equally real. All of them equally convinced of their own singularity, none of them aware of the others. And the universe is not losing any of them. The universe does not choose. The universe does not discard. The universe keeps all of it, all the branches, all the versions, all the paths, in the structure of the wave function, as real and as permanent as anything that has ever existed. Nothing is lost. Not even the things that feel lost. Not even the mathematician who became a weapons planner. Not even the physicist who was dismissed by the most powerful man in his field and quietly left, without drama, without a public word of complaint, and spent the rest of his short life in a different building, doing different work, in a house where his children barely knew him. Not even him. The wave function carries Hugh Everett III in every branch where he existed, perfectly preserved in the mathematics he spent his most important years writing down. Still right, still branching, still inhabiting the universe exactly as he described it. In every branch, the equation is true. As you close your eyes, as your breathing slows, as the quantum events in your neurons continue their silent, branching through the long hours of sleep, know that you are inside the theory. You are a branch. You are reading the mathematics from the inside. The universe is not something you are observing from outside. It is something you are made of and part of, and something you are one specific, real, valid path through the extraordinary structure of everything that exists. In every branch, the equation is true. And somewhere, in the structure of everything that is real, in the complete, perfect, unforgetting wave function of the universe, Hugh Everett III is still calculating. We have mentioned decoherence several times now, and it deserves a more careful treatment. Because decoherence is not just a word that many worlds uses to make itself sound like it explains something. It is a precise, experimentally confirmed physical process that was worked out in mathematical detail through the 1970s, 1990s. It is one of the best confirmed predictions of quantum mechanics, and it changes the picture of what many worlds is actually claiming in important ways. Start with what decoherence is not. Decoherence is not wave function collapse. Decoherence does not make superpositions disappear. After decoherence, the different branches of the wave function are still there. They are still real components of the total quantum state of the universe. Decoherence simply makes the different branches unable to interfere with each other. The physical reason is entanglement with the environment. When a quantum system in a superposition interacts with its surroundings, with air molecules, with thermal photons, with the fluctuating electromagnetic field, with the gravitational field, with anything at all, each component of the superposition becomes entangled with a different environmental state. The spin-up component of an electron becomes entangled with one configuration of nearby air molecules. The spin-down component becomes entangled with a slightly different configuration of those same air molecules. The two branches of the wave function now include not just the electron, but the entire local environment. For the two branches to interfere, for quantum effects to be visible, you would need to reverse all of this entanglement and bring the two environmental configurations back into perfect alignment. For a single air molecule interacting with a single electron, this might be feasible in principle in a carefully controlled laboratory. For the actual trillions of air molecules in a room, at room temperature, each of which has had its state slightly perturbed by the entanglement, reversing the decoherence would require a degree of control over the environment that is not practically achievable. Not forbidden by any physical law, but practically impossible by the same kind of impossibility that prevents a glass of water mixed with a drop of ink from spontaneously unmixing. The timescale for decoherence depends on the size and mass of the system and the strength of its coupling to the environment. For a single atom, quantum coherence can persist for milliseconds or longer under laboratory conditions. This is the regime that quantum computers must operate in, and why quantum computing requires extremely careful isolation from environmental noise. For a grain of sand, the decoherence time has been estimated at around 10 to the minus 23rd seconds, a timescale far shorter than any physical process we can observe. For a human being, the decoherence time is shorter still, by many more orders of magnitude. What this means for many worlds is precise and quantitative. The branching of the wave function into separate, classically behaving worlds is not a vague philosophical gesture. It is a calculable consequence of the Schrödinger equation applied to systems interacting with realistic environments. Given the density of air molecules in a typical room and the mass of any macroscopic object, decoherence theory predicts that superpositions will separate into effectively non-interfering branches on timescales so short that they are, for all practical purposes, instantaneous. The separate classical-looking branches that observers inhabit are not postulated, they are derived. Wojciech Zurek has been particularly careful about a phenomenon he calls einselection, environmentally induced superselection. The environment does not decohere all superpositions equally quickly. It preferentially and most rapidly decoheres superpositions in specific bases that depend on how the system couples to the environment. For massive objects, this is the position basis. Position is what couples most strongly to gravity and to electromagnetic interactions. An object at a definite position perturbs the gravitational and electromagnetic fields in a specific stable way. The environment effectively measures position continuously and with great precision, and superpositions of different positions decohere fastest. This explains something that had always been philosophically mysterious about the quantum to classical transition. Why the classical world has the particular structure it does. Why we see objects with definite positions, definite velocities, definite spatial extensions at the scales of ordinary experience. It is not because quantum mechanics stops applying at some scale. It is because position is the degree of freedom that the local environment preferentially selects and stabilizes through continuous entanglement. The classical world is what quantum mechanics looks like when filtered through the environmental entanglement that decoherence produces. Now let us think about what this means for the experience of branching. Suppose you are a physicist who has just measured the spin of an electron. The electron was prepared in a superposition of spin up and spin down. Your detector registered a result. You looked at the detector. The result entered your visual system, converted to electrical signals in your retina, transmitted along your optic nerve, processed through your lateral geniculate nucleus and visual cortex, distributed to your parietal and frontal cortices for interpretation and working memory, eventually becoming part of a conscious experience. At every step of this chain, decoherence was operating. The quantum branching that occurred when the electron interacted with the detector happened on timescales of fractions of a picosecond. By the time any information about the electron's state had propagated through even the first few atoms of the detector, the branching was complete and effectively irreversible. By the time the signal reached your eyes, the two branches, the you who sees spin-up branch and the you who sees spin-down branch, had been separate for an enormously long time by quantum standards. What you experience is what any observer inside a single branch experiences: a definite result. Spin up or spin down. One answer. No sense of ambiguity, no experience of superposition, no feeling of being in multiple states simultaneously. The branching happened. It happened irreversibly, long before any conscious experience occurred. You are already, by the time consciousness registers anything, deep inside one branch, surrounded by an environment that is fully consistent with that branch and contains no accessible information about the other. This is why Everett could say, with complete accuracy and without self-deception, that he didn't feel himself split, not because the splitting doesn't happen, because by the time quantum branching propagates to the scale of conscious experience, the branches are so thoroughly separated by decoherence that the observer inside any one branch has a completely ordinary classical experience of a single definite outcome. The splitting is real. It is simply entirely invisible from the inside of any branch. Let us also address what you means across branches, because this question does not get asked clearly enough. After a branching event, there are two distinct physical configurations of matter, two versions of the world, each of which is continuous with what existed before the branching. Both have your memories up to the moment of the event. Both have your physical body in states that diverged at the moment of the quantum measurement. Both will continue to have experiences, make decisions, live lives, form new memories. Both are, in every measurable and experiential sense, you. Many Worlds says, both are real. There is no privileged true you that survives the branching. The concept of a single, unique, persisting self that threads through time as one continuous entity is an approximation that works well in a world where quantum branching is effectively invisible. The self does not survive branching as a single thing. it branches. There are now two selves, each real, each continuous, with the pre-branching self, each unaware of the other. You are, right now, one path through a tree with more branches than any number language has words for. Every quantum event that could have gone differently in your history. From the moment of conception forward, every quantum event in the development of your nervous system, every quantum event in the neurons of every ancestor you have ever had, every quantum event since the Big Bang that was entangled in any causal chain that eventually led to you, all of that branching history has produced the specific version of you that is here, in this branch, at this moment. And all the other paths are equally real, equally occupied, equally convinced of their own uniqueness. The Born rule problem is the most technically serious challenge to many worlds, and it deserves a fuller treatment than it usually receives in popular discussions. The critics who raise it are not simply being difficult. They are pointing to a genuine conceptual gap that took decades to address rigorously. The Born rule is the rule that connects the wave function to probabilities. It says, the probability of measuring a particular outcome is equal to the squared modulus of the corresponding amplitude in the wave function. If the wave function of a two-state system is alpha times state 1 plus beta times state 2, the probability of measuring state 1 is the absolute value of alpha squared. And the probability of measuring state 2 is the absolute value of beta squared. This rule has been confirmed by every quantum mechanical experiment ever performed. It is one of the most precisely verified rules in all of science. In many worlds, all outcomes happen. The branch with state 1 is real. The branch with state 2 is real. No selection occurs. So when a physicist in the spin-up branch says the probability of getting spin-up was 50%, what does that mean? If all outcomes occurred, in what sense was any outcome probable or improbable? Everett addressed this in his original thesis. His argument was that the relevant concept of probability in many worlds is the relative measure of the branches. Branches are not all equally weighted. Each branch has an amplitude associated with it, and the squared amplitude gives the branch's measure its weight in the space of all branches. An observer who performs many repeated measurements will, in branches with near certainty measure, find frequency distributions that match the Born rule probabilities. The Born rule is recovered as a statement about branch measures rather than about objective single outcome probabilities. Critics pointed out that this argument seems to presuppose what it is trying to prove. To say that high-amplitude branches have large measure and therefore most observers find themselves there requires already having a concept of probability defined over branches. The argument has the uncomfortable circular quality of a justification that works only if you already accept the conclusion. David Deutsch attacked this problem from a fundamentally different angle in 1990. Rather than trying to derive probability from branch counting or limits, he used decision theory. He asked, what should a rational agent who believes many worlds is true do when faced with a quantum gamble, a situation where a quantum event with known wave function amplitudes determines what happens to them? He showed, using an axiomatic framework for rational preferences, that a rational agent should value quantum branches in proportion to their squared amplitudes. The Born rule emerges not as a statement about objective probability, but as the uniquely rational way to act in a branching universe. David Wallace extended Deutsch's argument into a rigorous formal result across a series of papers in the 2000s. Wallace's theorem shows that any agent with consistent preferences over outcomes in a branching quantum world, preferences that satisfy several natural axioms of rationality, will assign decision weights to quantum events that are mathematically equivalent to Born rule probabilities. If you want to act rationally in a many worlds universe, you must use the Bohr rule. It is not a postulate about nature. It is a theorem about rationality. Critics remain. Some argue that the rationality axioms that seem compelling in a non-branching context have no compelling justification in a branching one. Some argue that the approach shows only that rational agents should act as if the Bohr rule were true, not that it is true in any observer-independent physical sense. Some argue that the approach is question-begging at a deep level. These objections are real, and the debate continues in the philosophy of physics literature. But the important point is that many worlds is the only interpretation that has seriously attempted to derive the Bohr rule from something deeper rather than simply assuming it. Copenhagen makes the Bohr rule an axiom. Pilot Wave builds it in through the equilibrium distribution of hidden variables. Relational QM and Cubism reinterpret it as a statement about agent beliefs. Only many worlds, through Everett's original argument and its development by Deutsch and Wallace, attempts to explain why the Bohr rule is what it is. That attempt may not be fully successful, but it is more than any other interpretation has managed. Mark Everett was born in 1963, when his father was 2 years old, and Lambda Corporation was less than a year from being founded. He grew up in the house in McLean, Virginia, a comfortable house in a quiet suburb with a man who was, by every account from Mark himself, essentially a stranger. This is not a story of cruelty or violence. It is something quieter and in some ways harder to describe. The elder Everett was simply elsewhere. Not in body, he came home, he ate dinner, he was physically present in the spaces of the house. But the quality of attention and engagement that constitutes a real relationship between a parent and a child was located somewhere else entirely, in the calculations, in the models, in whatever Lambda was working on, in the interior of a mind that found the problems more vivid and compelling than the people. Mark has described his father across many interviews as a ghost, not the protective kind, not the warm, watchful ancestor, the cold kind. A presence that registered mainly as absence. The space where a father was supposed to be, occupied by someone you could see, but couldn't quite reach. The irony of this description, given what his father's theory says about the universe, is almost too much to absorb calmly. The man who proposed that nothing is ever lost, that every version of every event continues somewhere in the wave function, that the universe never forecloses a possibility, this man was, in his own home, a closed door. Nancy Everett managed the household, raised the children, and lived with the specific loneliness of being married to someone whose real life was happening in another room. She stayed. Through the drinking and the working and the silence, through the years when the physics work was dismissed, and the later years when it began to be taken seriously. She was there when Hugh died in his office at 51. Elizabeth Everett Liz was the elder child, and the one about whom the least is publicly documented. She inherited her father's intensity and, by several accounts, his difficulty with the ordinary social requirements of daily life. She lived outside the public view that eventually formed around her brother's music career. After her father's death in 1982, she carried the particular grief of mourning someone you were never quite given the grief of losing a person who was never quite there. In 1996, at 39, Elizabeth died by suicide. She left a note. The note said she was going to find her father in a parallel universe. Sit with that for a moment. Whether she meant it as genuine belief, whether in her last hours she had found some version of her father's theory as a real comfort, a logical argument that he still existed somewhere we cannot know. Whether she meant it as bitter commentary on the man who had proposed infinite worlds while failing to inhabit the one he shared with her, we cannot know. Whether it was something else entirely, some private meaning that died with her, we cannot know. What we know is that the man who described the structure of infinite branching realities had a daughter who, at the end of her life, invoked parallel universes to describe where she was going. And this is either the most heartbreaking possible convergence of a physicist's ideas with his family's tragedy, or the most devastating commentary on the cost of his particular kind of genius. Mark Everett turned his family into music. The Eels catalogue is, across 3 decades and many albums, an extended meditation on loss and absence, and the particular grief of losing people who were never quite fully present. The 1998 album Electroshock Blues, written after his sister's death and his mother's terminal cancer diagnosis, is one of the most personally devastating records in modern music. The sound of a man trying to process grief that cannot quite find its object, because the objects were never quite what they were supposed to be. In 2007, Mark participated in a BBC documentary about his father's physics. He walked through the Princeton physics department. He met physicists who spoke about Hugh Everett with the reverence that physics had finally, decades too late, learned to apply. He said it was the first time he had any real sense of who his father actually was. The father he discovered through the documentary, brilliant, obsessive, certain of his own correctness, indifferent to social convention, completely committed to the integrity of the mathematics regardless of the human cost, was recognizable to him. It was the man who had lived in the house, viewed from a different angle. The physics was Hugh Everett's real life. Everything else was secondary. And the physics was right. In every branch of the wave function, the equation holds. The families that formed around the man who wrote it down paid the price of his distance in each one. And the science independent of him, indifferent to his personal life, generated by the mathematics he had correctly understood, goes on being right in every branch, forever. Deutsch's answer: the computation happened in the branches. The quantum computer is not doing 2 to the 100th computations in a single physical system. It is doing 1 computation in each of 2 to the 100th branches of the wave function, and the interference between those branches at the end of the computation is what produces the measurable answer. The quantum computer is not a machine that processes information faster than a classical computer. It is a machine that harvests the results of computation that happened in an enormous number of parallel branches of the universal wave function. This picture is not just philosophically satisfying. It is physically precise. The quantum algorithms that achieve exponential speed-up over classical algorithms do so by carefully orchestrating interference between branches, by designing the computation so that branches corresponding to wrong answers interfere destructively, and branches corresponding to correct answers interfere constructively. The design of quantum algorithms is literally the design of interference patterns between branches. You can describe all of this without ever saying the word branch or invoking many worlds. You can say instead that quantum algorithms exploit quantum superposition and interference, and that these are mathematical features of the wave function that produce correct computational results. This is true, but it is the description of what happens, without an account of why. The why, the physical reason quantum computers can process exponentially many configurations with finite physical resources, is provided most naturally by many worlds, because the configurations are genuinely present in genuine branches doing genuine computation. IBM has quantum computers with over 1,000 qubits. Google demonstrated quantum advantage over the best classical algorithms for specific computational tasks in 2019. Quantum error correction, which is required for large-scale fault-tolerant quantum computing, is being actively developed. The technology is real, it works, and its power comes from quantum superposition from the same mathematical structure that in many worlds corresponds to parallel branches of the wave function doing parallel computation. Every time a quantum computer returns a correct answer, something computed in those parallel configurations. Whether you call them branches of the wave function or simply superposition with no ontological commitment, the mathematics is the same. Many worlds just takes the mathematics seriously as a description of what is physically real. We have been discussing physics and history and tragedy and mathematics. Let us come back to the scale of a single person, lying in the dark at the edge of sleep, carrying all of this. If many worlds is correct, and it may be, more may be, more physicists take it seriously than have ever taken it seriously before. Then certain things follow about your situation right now that are worth sitting with. Every thought you have had today involved quantum events, not in some distant, irrelevant sense, in the precise sense that the biochemistry of your neurons has quantum mechanical components. Ion channels in your cell membranes open and close probabilistically. Molecular processes in your synapses involve electron transfers that are governed by the Schrödinger equation. The random component of every probabilistic molecular event in your brain is in many worlds a branching, a creation of new versions of the world, each containing a version of you. The decisions you made today, the ones that felt genuinely open, the ones where you could have gone either way, may have had quantum components at their roots. Not necessarily. Much of the apparent randomness of human decision-making is classical chaos rather than quantum indeterminacy. But some of it, filtered down through the chaotic amplification that complex nonlinear systems perform, may have originated in quantum events. In those cases, in many worlds, you did go both ways. One version of you made the choice you remember. Another version made the other choice, and is right now, in their branch, not listening to this, making whatever life that choice opened up. This is not something that should make you feel less real. You are completely real. You are the version of you that is here, in this branch, with these experiences, with this sequence of choices and outcomes that constitutes your particular life. The other versions are equally real, but they are not more real. Branches are not ranked. They do not compete. They coexist in the wave function, each complete, each genuine, each unaware of the others. The comfort in this, if there is comfort, is not the comfort of knowing you will be okay. Many worlds makes no guarantees about any individual branch. Some branches of you are having terrible nights. Some are in better situations than this one. The wave function keeps all of them. The comfort is something more structural. It is the comfort of knowing that the universe is not choosing against you. The universe is not selecting from among possibilities and discarding the rest. Everything that could happen is happening, somewhere, in the mathematics of the wave function. Every version of your life that quantum mechanics permits is real. Not lived by you, lived by a counterpart of you. Continuous with you, up to the moment of branching, diverging from there. You are not the only path, you are one path, specific and real, and yours, through a structure that contains all the paths. The other paths are not your failure or your loss. They are simply other paths, equally valid, equally real, equally inhabited. As you close your eyes tonight, the branching continues. The quantum events in your neurons do not stop when consciousness dims. They continue through sleep, branching silently, in the dark, while you are unaware. By morning, you will wake up, one version of you will wake up into a world that is one specific branch of all the branches the night has generated. You will not know what the other branches look like. You will have no memory of them. You will simply wake into this one, as usual continuous with yesterday's version of yourself, carrying forward this specific life. That is what every morning is. That is what every day is. You, threading one continuous path through the branching tree, aware only of the branch you are on, living fully in it, each day a continuation of the one before. Hugh Everett understood this better than almost anyone. He understood the mathematics of it, the full scope and implication of what the equation said about the structure of existence. He understood it, and he was dismissed. And he lived the rest of his life in a different room, doing different work, and died before the recognition arrived. In the branch you are in, tonight you heard his story, and the equation he wrote, the one he was right about in 1957, and right about when he died, and right about still goes on being true. In every branch, describing the structure of everything, indifferent to whether anyone has noticed. The wave function does not need to be recognized to be true. Good night. The branching continues. You are inside it, and you are exactly, precisely, completely where the mathematics says you are.